if you have a double integral, you have region D, you think of this function as a density function, and you simply think that you're evaluating the mass of an object occupying this region where this function is a density function, right? And likewise, if you have a three-dimensional object which occupies some region E, you can think of the triple integral with a general function f as the mass of that object. You see, so that's the way to interpret it. So this is the total mass of a solid E with mass density function f. Any questions about this? All right. So our last topic in this chapter about integration is about general coordinate systems. And the general change of variables. We have already discussed some new coordinate systems in 2- and 3-dimensional spaces. We have talked about the polar coordinate system and we talked about a spherical coordinate system. Also cylindrical, but cylindrical in some sense. It's not really a new coordinate system. It's really more of a kind of a cousin of the polar coordinates. So now we would like to talk more systematically about different coordinate systems in 2- and 2-dimensional space. We can also do it in 3-dimensional space, but we'll just focus on the 2-dimensional space. In 3D, the conceptually it's the same, but the calculations are much more complicated. So we'll mostly confine ourselves to the 2-dimensional case. And as always, when we talk about this conceptual matters, it's always good to look at a simplified version, which in this case would mean just single integrals, integrals in one variable, and see how things work for single integrals. So let's recall how this works. Change of variable in a single integral f of x dx. So we know how it works. We simply we write x as a function, let's say g of some new variable u, and then what we do is we substitute this g of u instead of x in the integral. But in addition, we realize that dx is not du, but rather dx is g prime of u du. So what it means is that it would be wrong to just write the integral as f times du, but instead there is this additional factor, which is g prime of u. So we recognize that even in one dimensional case, there is this additional factor. And this factor actually should be thought of as being conceptually the same kind of object, the same kind of phenomenon as the factors which we discussed in the case of polar coordinates, namely the factor r, and the factor which we discussed in the case of spherical coordinates last time, which is rho squared sine phi. So these are all brothers in some sense. So they all appear for the same reason. I mean, although this is a one-dimensional case, this is a two-dimensional case, this is a three-dimensional case, but all these factors are essentially, they are kind of distortion factors, the area or volume distortion factors, which happen due to the fact that we introduce a new coordinate system. So our task right now then is to understand what exactly this factor is in the case of a most general coordinate change, not only in the one-dimensional case, but in the case of 2 and 3 variables. And like I said, mostly 2 variables. You see? So we would like to develop a formalism of change of variables, but for double integrals. That's what we'd like to do. For which this polar coordinate case will be just a special case. So let's try to figure this out. See how this works. So in the one-dimensional case, we have a given variable x, and we have a new variable u, and we have a law which allows us to express one of them in terms of the other, and that's this formula x equals g of u. But let's try to think of something similar in R2. So in R2, we have two given variables or coordinates, x and y, and we would like to introduce two new coordinates. Suppose we introduce new coordinates. Let's call them u and v. So here's an example. Polar coordinates, something we have learned already. uv, as this new coordinate system, is our old friend polar coordinate system. So u and v are r and theta. So when we do that, when we say that we have introduced a new coordinate system, what do we mean by that? We mean that we can express each of the old coordinates x and y in terms of these new coordinates in a one-to-one way, in a way that establishes a one-to-one correspondence between points with x, y coordinates and points with uv or r theta coordinates. In the case of polar coordinates, we know that those formulas, and we know that for every r and theta, where r is a positive number and theta is between 0 and 2 pi, we have a particular value of xy, and conversely, so it's a one-to-one correspondence. It's not, strictly speaking, correct what I said, because of the special point 0, the origin, point O, the origin, for which if r is equal to 0, then theta is not well defined. So except for this one point, this map, which I would like to think of this formulas as giving me a map, a correspondence from between two coordinate systems. This is our true physical coordinate system, xy. This is what we see. This is the blackboard, and this is how we would represent points on this blackboard. And here is a kind of a fake, auxiliary, imaginary coordinate system with coordinates r and theta. All right, let me write like this. In fact, many of you will recognize that we have used this before when we try to draw parametric curves and polar coordinates. We did use this kind of coordinate system. So it has nothing to do immediately with the plane, because the way a point here will give us a point on the plane is through these formulas. But I would like to think of these formulas as giving us a map from this auxiliary coordinate system, this imaginary coordinate system which we have in our head, which doesn't really exist, to the real coordinate system on the physical coordinate system on this physical plane. So for example, let's say I take the region where theta goes from 0 to pi, and r goes from 0 to 1. So this is a very simple region on this imaginary plane, right? It's a rectangle. But what does it correspond to in the physical world? What do you think? Circle. Okay, close. Warm. So The circle will come if we fix r. If we just look at this interval will correspond to the part of the circle of radius 1, which lies above the x-axis, because I said from 0 to pi. If I said from 0 to 2 pi, it would be the entire circle. But because I said from 0 to pi, it will be half a circle, right? Everyone agrees with that? Okay. But that's not the entire region, right? The entire region is composed not just by this interval, but also by all other intervals which lie beneath it, right? And so those intervals will correspond to circles of smaller radius. Right? And so altogether, here they give me this rectangle. But in the physical world, they give me this half a disk, upper half of the disk of radius 1. So you see something very interesting happened under this transformation. We started out with a rectangle, and we ended up with upper half of the disk. And I would like to say that these formulas give me a transformation from this region to this region. What do I mean by this? I mean that each point here will correspond to a particular point in here. And in fact, this correspondence is 1-to-1. In other words, no 2 points will go to the same point. Right? And like I said, this is almost true. Unfortunately, strictly speaking, it's not true for this interval. This entire interval where r is equal to 0 will go to this 1 point. So there is a subtlety. But the point is that we are studying here a two-dimensional region, and something bad happens on this interval, which is one-dimensional. This is what mathematicians call measure 0. It's not measurable. Its measure is negligibly small. It's actually 0. So as far as computation of integrals is concerned, it's not going to change anything. Okay? But if I wanted to be more precise, I would take, say, not this rectangle where r goes from 0 to 1, but I could instead take a rectangle where r goes from 1/2 to 1. Right? Then I would get, instead of upper half of the disk, I would get upper half of the annulus with the shorter radius 1/2 and the larger radius 1. So if I do that, actually, the transformation becomes less mysterious. You can certainly believe that I can transform this strip into this. What I do, I kind of twist it. That's what this transformation given by this two formula does. It kind of twists and expands and stretches in a certain very controlled way the fabric of this original domain to create a domain in the physical world. That's what this information is. And then if you think about the big one, it's sort of if you get closer and closer to this red part, it becomes closer. The way I stretch it is I stretch it on this side in the same way, but I stretch it on the lower side. Not stretch, but in fact squeeze to make it shorter and shorter and shorter. And as I approach here, actually the whole thing opens up into half of the disk. You see what I mean? You guys see what I mean? Yeah? Okay. So this is exactly the kind of formulas I'm talking about. This is a one-to-one transformation, one-to-one. So each point here corresponds to a point here, and conversely, each point here corresponds to one and only one point here. When I'm in this situation, I would like to be able to write a double integral of a given function f of xy dA as an integral with respect to u and v. And of course, so I'm kind of in the same situation as I was when I talked about the one-dimensional case. The first step would be to substitute the formula for x and y in terms of the new coordinates. So this would be, let's say, in general, here I have x is r cosine theta. So it is some function of r and theta. But in general, if I have a coordinate system uv, not necessarily polar, but more complicated, I'll give you an example in a minute of another change of variables like this. Let's say this will be some g of uv, and this will be some h of uv. So the first step would be to just substitute g of uv and h of uv instead of x and y, right? And then just write du dv. But this is not enough. The point is that there is always an additional factor. There is always a distortion factor here, which we are not going to calculate. An example of this factor is the factor r, which we have found in the case of polar coordinates. So for polar, we get r, and then we get dr, d theta. What we want to do is to have a more conceptual way of deriving this factor, not just for the polar coordinate system, but for a more general coordinate system uv, this factor. Okay? And of course, it's easier to explain having a particular example in mind. Well, here's one example, polar coordinates, but in polar coordinates we have already calculated what happens. You have a question? Yes? You're asking, would this have the same area as this? The answer is no. I'm sorry? Very good point. So this is a very good question. So when I say one-to-one, doesn't it already assume that it's going to have the same area, right? And the answer is no. And it's very easy to see that if you have, if you buy a garment which stretches, you can see immediately the answer, right? Unfortunately, none of what I'm wearing today can do the trick. But you can imagine that you have something which is stretchable. Maybe no. Oh, okay, let's just work with your imagination. You stretch it, right? A stretch is a perfect. What? This. Yeah, but my hands are. I don't want to. But that's a good. Can I use yours? No. But you see what I mean. Okay. So let's just use our imaginary clothes. So when you stretch is a perfect example of a change of variables because there is a one-to-one. Each particle, we don't create any new particles, right? Clearly, it's just each point goes to a particular point and it's one-to-one. It is like, okay, it's even easier to do in one-dimensional case. You can stretch an interval and make it, just say a map x goes to 2x. Everything gets stretched by a factor of 2, right? So it is one-to-one. But when you stretch, the area becomes bigger, right? So just the fact that it's one-to-one correspondence doesn't mean that the areas stay the same. And that's exactly what we're fighting for. This factor is precisely the distortion factor for the area. But the point is, which is maybe not immediately obvious, is that it would not be a good idea to actually measure this area and then measure this area and take the ratio of these two areas, right? But it would be okay if our function, which we were integrating, function f, if we chose the function 1, then we would just be calculating the area itself. And so if the area was something, the true area would be this, and the area which we would naively think is correct in the imaginary r theta coordinate system would be something else, and there would be some distortion factor between them, right? But that's not a good way to go because you see, when I make this transformation, the distortion factor is not the same everywhere. Because I explained, for example, that on this guy, let's look at this guy at the top interval becomes the part of the circle, segment of the circle radius 1, right? Whereas this guy, which has the same length, on the imaginary coordinate system, it becomes part of the circle radius 1/2. So certainly this is shorter than this. So our distortion is not like just stretching, but it's kind of stretching in different way in different places. So what we need is a local distortion factor. You see, like a local distortion factor, which in other words, we want to see not how this area gets distorted, this entire area gets distorted, but we want to see how this very small area around a particular point gets distorted. And that's the local distortion factor, and that's exactly the factor which we'll put here. Let me see. Any other questions? To see how this works, maybe it's better to. Sorry, you have a question? No. All right. So I want to give you another example of coordinate change before we get to calculating this factor, just to so that we have sort of a better variety of examples. Okay. So here's the second example, which is actually straight from the book. It's And this I want to use as a kind of motivation for everything we're doing right now, because perhaps for you it's not so clear yet why we are discussing this issue. But, well, polar coordinates is already a good illustration because we know the sum of the integrals become much simpler in polar coordinates. But here's another example where the coordinate system of choice is not polar coordinate system. So this is 15.9, number 20. And so let's say you need to calculate this integral over some region D, where D is described as follows. D is bounded by lines x minus y equals 0, x minus y equals 2, x plus y equals 0, and x plus y equals 3. Actually, so this is x plus y equals 0, this is x minus y equals 0, this is x plus y equals 2, or x minus y equals 2, this is negative 2. And then there is another one which goes like this. This is 2, this is 3. So it is actually a rectangle, because these two planes are parallel. Well, my picture is not so great, but they should be parallel, and these two should be parallel also. Right? So it is actually a rectangle, but it's a rectangle which is rotated. So first of all, if you try to do this integral in the usual way by projecting onto the x line or projecting onto the y line, it's going to be difficult because you see that first of all you have to break it into pieces, and then the bounds will be functions, will be some not very complicated but linear functions. But then you look at the integrand and you see that it's going to really look awful if you try to do this. Okay. So what this picture immediately suggests is that we should try to find another coordinate system in which this integral will simplify. And what is this coordinate system? Well, what if I told you that instead of calculating this integral, you would have to calculate the integral of u times e to the I want to say v times u times v du dv, where over some region d prime, where d prime would be simply u going from 0 to 2, in a slightly different way, would also be a rectangle, but this rectangle would be turned in the right direction. So this would be u and v, and this would be 2 and 3. You see, this surely is much easier to calculate, right? Because this immediately breaks into iterated integrals, and you find the answer right away. So what have I done? How can I get from this integral to this integral? I simply introduce new variables, u and v, where u is x minus y, and v is x plus y, right? If I do that, then my bounds, which were x minus y equals 0, become just bounds u equals 0 and u equals 2, right? Which is what I did here, from 0 to 2. And also v from 0 to 3, which is what I did here. So the region simplifies. It becomes, we turn it so that it really stands straight like this. And finally, the function simplifies as well, because x plus y becomes v, and x squared minus y squared I can write as x minus y times x plus y, which is u times v, right? But it is not true that this integral is equal to this integral, because, as I said, there has to be some factor, which is introduced, here. And to understand why we should introduce this factor, it's very easy to look at the map, the transformation. So we have here this rectangle in UV coordinate system. So see, this is an example also of this kind of transformation, but it's simpler because it's linear. And those of you who have taken or maybe are taking Math 54 will recognize a linear transformation. In fact, it is a rotation by 45 degrees, coupled with an expansion by square root of 2. So this is 2 and this is 3. And this formula gives me a map, because actually here I have expressed u and v in terms of x and y, but I can also go back and I can express x and y in terms of u and v. And I will find that x is u plus v over 2,